Hi, my name is Mattia Racca, PhD student from Aalto University. In this video, I will present you the work I've done together with Professors Ville, Kyrki and Cakmak on the interactive tuning of robot programs. End-user programming interfaces are becoming increasingly common on modern robotics platforms. These interfaces allow end users to compose programs out of discrete parametrized robot actions, with the number and the complexity of their parameters depending on the chosen design. Here, for example, we have a simple action, a linear motion, with two parameters, the goal pose to be reached and the speed used to reach the goal pose. While these interfaces are certainly more intuitive to use compared to traditional programming, they still present challenges for novice users. In this paper, we propose a method to aid the tuning of parametrized robot actions. Let's take a look at how these parameter values are usually specified. For certain parameters, like the goal pose of our linear motion, intuitive interfaces are available. For example, the user could set the goal pose by dragging the robot with kinesthetic teaching. For other parameters, however, like the speed of this linear motion, no intuitive or sufficiently reliable interfaces are available. Consequently, their tuning is often performed manually through GUI elements like sliders. This causes a time-consuming trial-and-error tuning process, where a parameter value is selected from the GUI for the robot to execute the action. If the parameter is not immediately correct, as it is often the case, the action needs to be reverted. The user then needs to select a new parameter value and repeat the process. So here is our idea. What if the robot would intelligently select the parameter to be tried out, asking the user only to evaluate their execution? If informative values are selected, the tuning should be consequently faster. We frame this tuning as an active learning problem, with the robot selecting informative parameter values and showing them to the user via the parametrized action to gather their feedback. To add flexibility to the tuned program, the active learning agent learns a range of feasible parameter values instead of a single correct value. Here is our tuning pipeline in action. First, the robot selects a parameter value and announces it to the user through the GUI. The parameterized action is then executed on the real robot. Finally, the GUI collects the feedback from the user. If more tuning is deemed needed by the active learning agent, the action is reverted and the process is repeated. Under the hood, we need to solve three sub-problems: how to model the parameter range estimation, how to update the current estimate with the user's feedback, and how to select informative values to try out on the robot. For the modeling, we adopted a Bayesian approach and placed priors over the action parameters. These priors can be extracted, for example, from programs authored by expert users. As the goal of our tuning is to estimate a range of feasible parameters, we derive the distribution of the lower bound and the upper bound. Here, you can see the prior for the speed of the linear motion in gray. In blue, you can see different choices of distribution for the lower bound. Regarding the model update, given the one-dimensional nature of the tuned parameters, we allowed users to provide directional feedback. The users could specify if our parameter value should be lower or higher, or if it is just fine after seeing an action execution. You can see here how the lower bound posterior is computed starting from the prior distribution, based on the query parameter value and the user feedback, telling that the robot should move slower. Finally, we have to select the parameter values that are beneficial to be tried out on the real robot. In this work, we adopted two active learning strategies: uncertainty sampling and expected divergence maximization, along with a random baseline. The picture shows you the working principle behind expected divergence maximization. For each possible parameter value, we simulate the computation of the expected posterior and compute the expected distance between the posterior and the prior through the Jensen-Shannon divergence. The query value with the highest expected divergence is expected to bring the most information to the model, and it is therefore selected. To evaluate our tuning approach, we tested its performance in simulation, first with synthetic priors and then with priors extracted from robot programs authored by expert users, targeting 4 tabletop tasks. To do so, we designed a simple domain-specific language for the Panda robot, with 5 parametrized actions. We then ran a small user study with 8 NOVICE users. In this presentation, I will focus on this user study. More details about the simulation experiments are of course presented in the paper. In the user study, the participants had to tune the parameter of a simple end-over task using 2 interfaces, a baseline interface with slider and our active tuning interface. The active interface would ask 3 queries per parameter of each robot action in the program, while with the baseline interface, the participants were free to decide how to tune the robot program. From the study, we observed how the participants were able to tune better and faster with the proposed active tuning interface. However, the active interface had a major drawback. The robot had a too strict control over the tuning process. While the active interface was perceived as useful at the beginning of the interaction, the participants preferred at the end the baseline interface because it allowed for a more customized result. Furthermore, the baseline interface was perceived as faster to use, even if it actually wasn't. The user study allowed us to identify several future directions. To solve the control issue, more discrete ways of suggesting tuning attempts should be implemented. For example, the informative parameter values could be highlighted over the GUI sliders, or the active tuning could be an on-demand feature. The current tuning pipeline requires the robot to execute and revert its actions after each tuning attempt. This is unfortunately still extremely time-consuming. One possible solution would be to move some of the robot actions executions to visualization or simulation tools to speed up the process. It is, however, not clear to us whether the users can reliably express feedback about certain parameters when the action is not displayed on the real robot. On the learning side, a clear improvement would be to allow the active learning to select which parameter to tune when a robot action has more than one parameter. Instead of the fixed number of queries of our current implementation, the learner would be allowed to spend more queries on parameters that are harder to tune. Another improvement would be to tune multiple parameters at the same time. On one hand, this would allow queries to capture the relation between different parameters. On the other hand, however, we don't know if users would be able to reliably express directional feedback in this scenario. Maybe a simpler but less powerful binary feedback should be used instead. Summarizing, in this paper we proposed a novel interactive tuning process for parametrized robot actions, framing the problem as an active learning problem. The experiments show the usability of this approach with NOVICE users, along with several interesting future directions. Once more, I thank you for listening. Please contact me by email if you have any question or feedback. Thank you.